Okay, good morning, folks, or good afternoon, good evening, again, whenever you're finding time to watch this. Um, we are going to now move into our second week of offsite learning. Okay, this is the first week where you won't have already had the notes that we're going to be using. So you'll need, okay, it's posted in the Google Classroom, but you'll need the chapter 12 notes. Okay, they're going to look like this. Now, I understand that's a lot of paper to print, a lot of ink to use. If that's an obstacle, again, there's nothing wrong with just taking notes on loose leaf as you go, but you do probably want to have a digital copy open so you can at least follow along with what I'm showing on the screen there. Okay, so chapter 12 is we're going to now look into the world of magnetism. And as we're going to learn, that's actually not that far of a departure from the world we were just in of electricity. Okay, yeah, let's just get right into it. Okay, so let's jump right in. A lot of the stuff I'm going to have to kind of show you, which I think is fun. I wish you were here in person to see it, but yes, better this than not at all. So, uh, what is a magnet? Or what are the parts of a magnet? Or what are the kind of things we need to know about a magnet as we get started? Well, the first thing is that magnets have two different poles. Okay, why poles? That's kind of the name we decided to give them, right? Just like why charge, right? Well, we called it a charge. Okay, why did we say one charge was positive, one charge was negative? Well, we kind of just we knew they were opposites, right? That's it. Doesn't mean anything about direction. Just means they were opposites. Now, same goes for a magnet. We call one end north and south. This does have more of a reason behind it than with the charges, where it was just kind of, oh, they got to have opposite names. With magnetic fields, okay, you might have an inkling already, right? Because of the direction that a compass, which is a magnet, points, right, we've kind of been drawn to calling one end the North Pole and one end the South Pole. So magnets have, just like the Earth, a North Pole and a South Pole. In fact, for Earth, the North Pole and the South Pole can also be thought of as magnetic poles, okay? Well, not thought of, they are magnetic poles. Okay, so what can be a magnet and what can't be a magnet? Because as you know, not all metals just stick together, right? And it's a very common mistake or a common misconception, right? Well into adulthood, a lot of people think this, and it's not a knock against them or anything, but it is kind of how we all as kids learn how magnets work is that, oh, they stick to metals, right? It's not true, right? Magnets actually, very few types of objects will stick to a magnet. In fact, only other what we call ferromagnetic materials will stick to another ferromagnetic object, right? We can also make magnets through, we can make an electromagnet, which we'll get to later as well. But I just wanted kind of to, right off the bat, remind or let you know if you didn't, okay, or remind you if you did know that A, not everything is a magnet, and B, not all metals will stick to magnets. They need to be what's called ferromagnetic, okay? Where does that ferro part come from? It comes from the Latin name for iron, ferrum, okay? Because iron is actually the namesake for ferromagnetism. Ever notice in the periodic table, it's got the symbol Fe, which doesn't seem to match with the word iron? Yeah, that's because it's the Latin one, okay? So just this idea of magnets having different poles, okay? We'll get to what is required for something to be ferromagnetic, but just want to get that out of the way right now. Not everything can be a magnet, and not everything can be attracted or repelled by a magnet. In fact, only magnetic things can. So how do we tell which pole is the North Pole and which pole is the South Pole? Well, much like when we were looking at charges, we kind of have to rely on how they behave, right? So if two objects, for example, repel, you don't actually know whether they are positively or negatively charged. All you know is that they have the same charge, right? It's a similar kind of idea here. We might know something is a magnet, but until we can see which way it reacts in regards to another magnet, then we don't really know which pole is which. So I'll show you what I mean here. Okay, so for example, here I've got a magnet suspended on a string. So in this axis, it's fairly free to move. There is going to be a bit of tension in the string that's going to stop it from doing too much. And I have another magnet here. This one's the same thing. I'll show you. I don't want to get too close because of the electronics in the computer, but notice the little N. So red is North Pole, and the little S, so blue, is the South Pole. Okay, now what happens if I bring the South Pole close to the other South Pole? Notice they repel away. And then when the North Pole side gets around, it wants to stay there, right? Okay. What if I now flip this guy so that the North Pole is nearby? Aha, now it turns the other way, okay? Fighting that tension in the string should eventually kind of come to rest. There. If I get too close, I can even make them stick, right? Okay. You can even kind of twist around. If I take the south, point it to the south, I can go around and around and around, never actually touching them, right? Until the tension in the string got enough that it was no longer able to, right about there. All right, so not unlike our law of charges, okay, opposite poles attract, like poles repel. And then it asks us, what does this say about the Earth's North Pole? Okay, so what does it say about the Earth's North Pole? Well, if you've ever used a compass, the North Pole of the compass, the red one, right, that's the North Pole, points towards what it's well attracted to, right? So where would the North Pole of the compass's magnet want to point? It would want to point to a magnetic south pole, right? So Earth's geographic North Pole is actually a magnetic south pole, okay? Oops. It's a magnetic south pole, right? It's a geographic North Pole because, well, we decide how geography works, but it's actually a magnetic South Pole. Uh, that's because we kind of decided these conventions before we knew enough about magnetism to properly distinguish them that way, right? And we already called that North, so we were kind of stuck with the fact that, whoops, we kind of named those wrong for our Earth anyway. All right, and then looking at this idea here that you cannot separate the poles, right? So you could separate the poles, but you're going to create new poles. So I'll show you what I mean with that there. But this is a good kind of image, right? If you take a north and a south, well, a magnet, so it has a north and a south pole, and you split it, you're not going to magically have something that's all north, right? Or all south. Notice how it just instantly becomes a new south pole over here and a new north pole over here. You can even split that up again and the same thing happens all over again. Even if you split it sideways, although that would never really do it anyway, right? But now you've got a north pole here and a south pole here. You've just got two magnets now. Okay, so for example here, I have, yes, it's a bunch of little magnets, but when I put them together, they essentially act as one large magnet, right? With a north pole somewhere and a south pole somewhere. Now, since this one wasn't nicely labeled by the manufacturers like this one was, right? There's no north and north-south pointing on there. We don't actually know. So how can we figure out? Well, we could bring it near another magnet whose poles we do know and see how they interact, right? So let's try this end here. Let's try this one. Okay, I'm going to bring it near the south pole of this magnet. Oh, look at that, attraction for sure. Okay, this magnet is actually much stronger. So you can notice, whoa, oops. Okay, it's totally stuck, right? And then if I bring the other end, okay, so this is definitely the north. Cool. Okay. So you might be thinking, okay, so if this is the North Pole, this is the South Pole, right? So that's distracting. What did I say? Okay, this is, yes, that's attracting. Okay, so this is the South because it attracted the North. So this is the South Pole on this end, right? Making this the North Pole. So you might be thinking, well, about halfway is where the North Pole becomes the South Pole. So hang on, I bet I could, what if I take off, what if I break this magnet, okay? North, no, south, south and north, right? So if this is all, if these three magnets all kind of compose the whole, the South Pole, then what if I were to break it? Then I should have a piece that's all south, shouldn't I? Right? If I were to break this off, this is the South Pole, this is the North Pole, right? So these three, if I were to break the last one off, that piece you would think would be all south. These are very strong magnets. Okay, so now I've got this piece that we suppose would be all south. So let's see what happens. If this piece is now all south, what's going to happen? Is it going to, okay, it is attracting north. That checks out. What does it do to this guy though? Nope, it's still repelling south. Okay, so what if I flip it around then? Is the other, so now I flipped it, is the other end now still a south pole? Nope, it just attracted to a south pole, right? So by splitting it, I did exactly kind of what the diagram in the notes showed you there. I went from one big magnet with a bunch of, with north and south, right? All the way through. By splitting it, I've just made now a smaller magnet with a north and a south, right? I don't magically have a piece that's all south. All I've done is make something with a different north and a different south. So as we saw, for example, with our electric field, we kind of need to pick a way to define the direction of the field and then sort of stick with it, right? So in the electric field, it was what would a positive charge do? In the case of our magnetic field, it's what is the direction that the North Pole of a test magnet would point? Okay, so if we put a test magnet into the field, which way would its north end point, its North Pole point, right? So you can often just think of it as a compass. A compass is a very good test magnet. In fact, that's kind of what we're doing when we're looking at the Earth's magnetic. When we are pulling out a compass, we are kind of doing that vibe check on the magnetic field that is the vibe and saying which way is the vibe at this point on Earth. Because if it's that way, then I know how to get to geographic north, which again is a magnetic south, right? So looking at this image here, which way would a test compass point? It would point that way, right? Here, that way, here, that way, right? Just imagine dragging a compass around at all these points. So I'll show you for real. Okay, so what I have here is, again, just another bar magnet. I've wrapped it in saran wrap. You'll see why in a moment, okay? I just want to we'll use this to kind of get a feel for the shape of a magnetic field. We're not going to worry about direction just yet, but magnetic field, like electric field, is a vector, so it does have a direction. We'll do something else with direction in a second here, okay? Now, if you care, this is going to be the North Pole, this is going to be the South Pole. That's not going to end up mattering because, again, we're just looking at shape, not direction, but it never hurts to know. And then the other thing I have here are some iron metal filings, okay? Iron is ferromagnetic, right? In fact, that word ferromagnetic, it comes from the Latin name for ferrum. Will respond to the magnetic field that we have here because of the magnet. So what I'm going to do, it's small, so it can really kind of be affected by it. I'm going to just sprinkle some on lightly, and we might reveal the shape of the magnetic field. That's so cool. Okay, now I want you to notice a couple things. Notice that at the ends is where it's really been drawn in. It's really sticking there. It's very kind of dense in there, right? We can see that these iron filings are kind of being aligned along the magnetic field lines, right? We don't know which direction the field lines point, but we can definitely see that the field lines are there.
I also just want to point out to you that look, pick a line that starts on one pole of the magnet. So, for example, on the north half or on the south half, doesn't matter. Trace it. Where does it end up? It ends up on the other pole, right? We'll think about direction later, like I keep saying, but as you look at this, okay, notice that every field line that starts on one pole finishes on the other. Even these big guys, you can kind of see there might not be enough room here, right? But it's very apparent here where we kind of have the halfway point, right? They start on the north, go to the south, start on the north, go to the south, or
Why don't you just watch what happens too while I kind of move the magnet around if you look at the iron filings. Notice how they kind of follow it there, okay? Pretty cool. So we can kind of see the magnetic field moving around. So what's it look like when we have two like poles kind of pointed at each other? Let's just see the shape of the field when that is the case. So here I have two bar magnets with the north poles nearest to each other. I'm going to go ahead and sprinkle. So you can see here in the field, in the middle between the two magnets, the field lines kind of meet and then diverge like that, right? They kind of go out like that and up and out like that. Pretty cool. Now, what about when we place two opposite poles near each other? Okay, let's take a look at what the shape of the magnetic field looks like now. Just going to give a little more room there in the middle. Attraction is so much there that the filings are just kind of going and sticking to the sides right away. There we go. So notice before they were just too close, and there was actually the iron filings would feel too great of a force, and they wouldn't sit on the paper there like I wanted them to show the field. So they were kind of just jumping to the sides there. Okay, so that's kind of how it looks when we have two opposite poles near each other when we look at the field lines. Right, notice over here, still happening on these magnets. These field lines still look the same, but then as the magnetic fields start to interact more strongly here, then we get some more interesting interactions. So instead of meeting and going like they did when we had opposite, right, they kind of bow and then repel. We have field lines going from one magnet over to the other. Another thing I kind of want you to realize here, and we use the filings to show you, don't forget, we often are drawing stuff on paper, right? Which kind of limits us to 2D representations, but don't forget, we live in a 3D universe, right? So those field lines are, right, in 3 dimensions. If I were to get some iron filings on there, you would see they are coming towards you and away from you as well, right? So when I have these sitting here, don't forget that there are field lines coming out of the page as well. Now, in what direction? Let's get to that. Okay, so again, key point, they leave north and they enter south. On their way through, they have to then leave north again, right? So for the most part, field lines are pointed towards south. The only place that's not true is within the magnet itself, right? Because they have to leave north again to then go around. So exit north, enter south, right? The density of field lines is called its flux. Again, that just means how strong essentially is the magnetic field. Flux technically means per unit area. So if you think of like a square, how many field lines, a 2D kind of square, if these are field lines, that would be a decent flux. What would a stronger flux look like? Just more per the same unit area, more field lines, okay? That's all that means. So flux, again, like with our electric field, how do we show a strong magnetic field? With more dense field lines, okay? How do we show a weaker magnetic field? With less dense field lines. So this question asks us here, predict where the magnetic field strength is the strongest and where it is the weakest. Justify your answer referencing the diagram. So where do you think, looking at this diagram, what jumps out to you as per strong point? So again, just like with our electric field, we show strength with density of field lines. So where are the field lines the most dense here? Well, essentially dense in this context means bunched up together, right? So look at that, pretty dense there, okay? Pretty dense there, at least compared to other places. Also pretty dense here, right? So I would say those are the places where it's strongest. Where is it weakest? Well, what's on the diagram, we just have to say, okay, where is it the most spread out, right? Where is it the least dense? So it's not great there, right? Not very strong there, or there, or there, okay? Remember though, this diagram kind of just ends wherever it feels like. This could go on forever and ever, right? It could go on up here. Technically, it's going to be even weaker. Over here, it's going to be even weaker, right? There's no kind of point where it just ends completely, but you can imagine these are going to get less and less dense as we move away from the magnet. Okay, so let's just do these for real. So if you want to open page 586 of your textbook, you can kind of follow along as we go. But just looking at the shape, or the quote unquote shape, and the direction of the magnetic field. Remember, for direction, we're going to need a test magnet. We'll use a compass. Okay, so when it comes to magnetic field direction, kind of like electric field direction, we need, well, and like gravitational field direction, we kind of need to think of the direction that some other test object would behave in a certain way. So you can see I'm being kind of careful with my words there, right? In a gravitational field, we said the direction a test mass would move, and yes, it always happened to be down, right? But then when we look at, and then we looked at electric field, it was the direction a positive test charge would move. Magnetic forces are a little bit weirder than electric forces or gravitational forces. So I'm going to be careful about talking about forces that are felt, but I am going to say, okay, we still have to define it in terms of the direction a test object kind of behaves in some way, right? So we say for a magnetic field, the direction of the field, because yes, it has a direction, right? We would say that it's the direction a test magnet would point its north end if free to move. So I know a type of magnet that is free to move, right? A compass. So let's take a look at the magnetic field around this bar magnet and see if we can kind of get some ideas about direction by looking at which way it points. So again, this is the north needle, okay? The black is the south needle. So right now it's sort of pointing to Earth's magnetic field. It's a little far away. This isn't a very strong magnet. Okay, but if I bring it down here, you'll notice, look at that. Okay, so notice north is not pointing towards north. North is actually pointing straight out of north. What if I bring it over here? Ah, now it's pointing towards the south, right? So there we go. Oh, do you see what happened in the middle there? Right at the very middle, notice that's where it kind of starts to switch. So look at that. As it goes, you can kind of see, and then I want you to compare with the iron filings below, right? Look at the orientation of the needle. Look at that. Look at the as it passes over the iron filings there. See how it's kind of keeping pretty tangential to those things. I actually, as I go across that path, notice it actually traces out the path of the field lines. It just now gives us a way to conceptualize direction. Okay, so we basically say that magnetic field direction is in the direction that a test compas's or a test magnet's north end would point. So right there, which way is the magnetic field? Well, it would be that way, right? It would be that way. That's how well, that's not going to work. That's how my test magnet, my compass, pointed, right? That way. Okay, see, it's pointing that way. So I can even draw it as an arrow. Okay, what about down here? Same thing, still pointing that way, right? As we already saw, okay, when it's at north, right, it points directly out that way, right? As we go this way, okay, it ends up pointing there. What about here? Well, it's pointing out that way. Here, oh, now it's pointing into south. Okay, what about over here, right? It's pointing directly in here, down into south, here, kind of out away, here. Okay, you can kind of start to get the idea. Notice that, right? It's always sort of, just going to keep going while I talk, it's always sort of coming out of north and then going towards south, right? It's coming out of north and then going to south. So I think of magnetic fields as leaving north, entering south. What about inside the magnet? Well, the magnetic field has to kind of continue, right? So inside the magnet, it kind of goes through to north and then out around to south, right? Exits north, enters south. So no matter where you put it will always be pointing kind of towards south away from north, or on its way from north to south is how I think of it, right? There it goes like that. And notice how it's along those field lines that we saw with the iron filings. Okay, so essentially it goes from north all the way around to south. Exits north, enters south. Right? And then in between, you can draw kind of smaller lines because this has still the North Pole still going to the South Pole, just along like our iron filing lines there. Okay, of course, this is getting kind of messy, but that's the idea. So there's our field at every point, just like our electric field, right? Just like our electric field, there is a direction at every point. There's a magnitude and direction of the magnetic field at every point in space. We can map it out a little bit with our compass, and with our iron filings, we can kind of see the shape. So we have the shape, we have the direction, we can sort of map out the magnetic field. And now to come back to my question about the 3D magnetic field lines, because remember, right, the iron filings are also standing up on edge on the end. I won't pick it up because I don't want to ruin it, but right, they're also coming kind of out this way. So if we have here, right, if now we know that magnetic field lines leave north, go towards south, right? They exit north, enter south. What do you think the ones look like that are coming towards the camera, right at your face right now? Well, they'd be leaving here, coming up, right, and then going back down south. And in fact, if I hold the compass here, okay, here, you can see that. See the red, the north is pointing up. That's the test compass or the test magnet telling us that the direction of the field is the way of test magnet points, right? And as I go over here, notice the red still remains that way. So over here, points up, okay, some point around here, okay? So even in 3 dimensions, this works, this direction convention. Now we sort of already got an idea for the shape, so to speak, of the magnetic field when we have two interacting like this, right? Here it kind of is again. What do we know about direction now that we can maybe apply a bit here? Well, remember, it leaves north, it enters south. So first, let's make a prediction. Which way should the magnetic field lines be here between these magnets? So these lines here. We can see that they're going from this magnet to that magnet. Okay, that part's clear. Which way are they, would we define them as going though? Are they going this way or are they going this way? Okay, well, as we know, we would predict that they leave north, enter south by convention, right? So leave north, enter south. So I would say between here, we would have field lines essentially going straight across, right? These ones bow out a bit because it kind of thinks about going to its own south, but then this one's much closer. So it says, nope, I'm going to go to that south, right? Same thing here. As we get up, it gets a little more bowed out a bit, right? Same thing down here. Okay. Eventually up here, we kind of get, whoa, all the way over, right? Now it's far enough away that it says, nope, I'm going to go to my own south pole because that's all field lines are doing. Leaving north, entering south, right? Leaving north, entering south. Okay, whoops, 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 whoops. Wrong, wrong, wrong. That way. Sorry. Okay. You can see the same things kind of happening here. Which way are these ones going, right? These are actually coming from north, going to south. So these are going this way, right? I keep saying this like we kind of taken it for granted. What was the whole point of this? To check it with our test magnet. So let's take our compass, our test magnet, and see. So remember the definition of magnetic field direction. How do we determine what direction the magnetic field has at a certain point? We'll place a test magnet there and see which way its north end points. So let's stick it there. Aha, there we go. Just like we predicted, right? Up here, okay, towards, I've just pushed the magnets a bit, so I've kind of changed it, but notice, hey, look, it kind of perfectly follows my field line I've drawn, somewhat. I kind of, right? Look at that. It definitely is following the shape. That's really cool to see. Look at that. Wow. Okay, right, over here. Again, these field lines are not going from the North Pole to the other magnet's South Pole. We can see they're actually going from this to its own south pole, right? What about these ones? Like I said, are they going from here to there or from there to there? Well, check. Aha, right? Because they exit north, enter south, that's the direction they go, right? Really cool. Okay, so here I've already done the iron filings for for two like poles that are near each other, right? So a north and a north. So these magnets are repelling each other right now. Okay, so what does the compass say, the test magnet say about the direction of the field lines? Well, you can kind of see it's a bit dodgy right here, right? It's kind of a interesting mishmash of field lines. That's because it is very, very sensitive, right? Just to a tiny displacement, it's kind of hard for it to say where just at that point there, right? Notice, okay, it flips, 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 right? So it's kind of vertical here, right? You can kind of see if I can find the point. There it is. It's kind of hard to find because it's so sensitive to being on either side. But right there, we kind of have these vertical lines, right? What about down here? Okay, again, vertical. Notice though, they're still pointed away from each north. So they're kind of and right? The field lines, if I go there, right? Leaving north, so it's kind of going like that, right? Kind of going like that. And then where are they going to go? They're leaving north, right? Leaving north. Okay, I can draw them there. That's not very well drawn, but you get the idea. Okay, leaving north. And where are they eventually going to make their way to? Well, to the magnet south, right? So in this case, that one's going on along. That one would be off the page. That's a big, long field line far away, right? But we can still see kind of these ones here, right? These ones here, these ones here, right? And again, I keep drawing just the one arrow, but remember, at every point, we could draw a direction. Every point along a field line, there's a direction, right? It's just kind of easier to show it's going that way, and at every point it's going in the same direction, right? And the same thing over here. If we go, okay, follows along the field lines. But still leaving north, entering south. We just have an interaction going on here from the two magnets, each with their own magnetic field, because they interact in the middle here. The field lines kind of crisscross, and we get this interesting pattern. But the direction convention doesn't change. It's still leaving a north and entering a south, leaving a north and entering a south. This is sort of the cause of the repulsion as well, right? The fact that these magnetic field lines don't want to go to the other side. They want to get away from that other north, right? They just left a north. They're not going to go towards the other north. Magnetic field lines leave norths. They don't enter norths, right? So the field lines definitely bow out away back to their own south poles. One last arrangement I want to look at here, okay? But I want you to pretend this well, not that it doesn't exist, but that it's kind of a horseshoe magnet. We used to have good horseshoe magnets here. There are not any currently in our physics lab, so I got to make do with this. Okay, so just kind of focus on this part, because essentially that tip end there will give you the same idea as a horseshoe magnet. And not just a horseshoe magnet, but also just the idea of two magnets with opposite poles somewhat kind of aligned, right? But on a horizontal kind of parallel axis here, as opposed to end to end like we were looking at before, right? Now we're taking those two opposite poles and going this way, right? So what do you think? I want you to make a prediction. Those field lines there, what do you think is the direction, the orientation of them? I'm just kind of going to spread them. I'm not changing anything. I'm just going to spread them so I can actually fit our test magnet, aka our compass, in there. Okay. Which way do you think they're going? Well, as always, magnetic field lines leave a north and enter a south, right? If it's just one magnet, they leave their own north and enter their own south. But if there's another magnet nearby enough, right, those field lines can just say, well, there's a south, I'll enter that south, right? And so, just like we kind of would have predicted, within these two, we have field lines that way, right? And then what about over here? Aha, they're leaving the north, right? They're leaving the north. Where do you think they're going? Where do you think those field lines are pointed? Aha, just like we would have expected. They're headed south, right? All the way along there, we can kind of trace it. Look at that. Look at that. It perfectly follows my arrow. Wow, that's really neat. Okay, up here, it's going over to its own, but remember, we're trying to kind of just focus on this, because we've seen that before. That's just one magnet kind of interacting with itself for the most part. Okay, so in between them, we have these kind of parallel field lines, always pointed from north to south. You can also look at a simulation. Right, so here I have a magnet. Nothing super interesting yet. Let's see inside the magnet first. So notice, okay, field lines, they leave north and they enter south. Leave north, enter south, okay? We can also show a compass. Let's see, how did we determine this field direction? Well, it was by saying, okay, if we had a test magnet, like a compass, right? What direction would its north pole point, right? And so notice wherever I drag it on here, it's kind of matching, right? Like we saw with the real life version as well here, but now I can visualize kind of the whole field directions all at once, okay? Notice here, leaving north, going around, entering south. Can also show Earth, okay? Look at Earth. So notice, right, south, the magnetic south is actually geographic north. So geographic north is actually a magnetic south, right? So if we take our compass, that's why a compass works. Why does it always point north, right? Because the field lines leave the North Pole and enter the south. So when you take your magnet and point its North Pole, it will take you north, right? So magnetic south is geographic north. That's why a compass shows us north. And remember, this field exists. Even if there's no test magnet, the field is there, right? It's just a test magnet allows us to kind of think about the direction. Much like the electric field, right? It's there. You just need some other object to feel it for it to be expressed. Doesn't mean it's not there when some other object isn't there. Last kind of idea for this topic is the domain theory of magnets. So The domain theory of magnets is essentially just a way of explaining why magnets kind of have the properties that they do. Okay, so the pieces are kind of here. I'm going to show you a video that I think does a really good job of kind of building up domain theory. They're going to talk about some things in this video that are we are going to get to later. They kind of brush over them very quickly. Don't worry, don't panic. That big thing I'm talking about is that a moving charge produces a magnetic field, right? And as it says here, more on it later, but for now, you just need to accept that, okay? So accept that a moving charge produces a magnetic field. That is kind of the first thing that you need to take to build up domain theory, okay? And then after that, it makes sense. If you can accept that, then the domain theory kind of follows, right? Remember, electrons are charged, so if they're moving, right, they produce magnetic fields. Okay, so let's just watch the video really quick, then we'll come back, look at the main ideas of domain theory. And before I start the video too, I just want to make clear, put you at ease a bit. This video is going to go a bit further into depth, well, quite a bit, way further into depth than you actually need to understand or are expected to know for Physics 30. It's going to talk about quantum mechanics, which we will talk a little bit about, but we haven't yet, okay? But the general overview it gives of domain theory, I think, is good. So if it's starting to lose you a bit, don't worry, it's going to come back. They're going to kind of break down the criteria, what all has to happen in order to make a permanent magnet.
If you take a piece of wood and put it next to another piece of wood, nothing happens. And if you take a piece of granite and put it next to another rock, still nothing. But if you take this piece of iron and put it next to this other piece of iron, magnet. Magnetic objects are able to magically attract at long distances because they generate magnetic fields that extend invisibly out beyond the object. But the mystery is this: where do magnetic fields come from?
Well, that's easy, Henry. We've known for a long time that electricity and magnetism are really just two sides of the same coin. Kind of like mass and energy or time and space. They can be transformed into one another. And in fact, a magnetic field is just what an electric field becomes when an electrically charged object starts moving.
That makes sense for explaining why a current of electrons flowing through a wire causes this compass needle to move, or how currents in the Earth's outer core generate the geomagnetic field. But a bar magnet or the compass needle itself are just pieces of metal without any electrical current running through them.
Or are they? At the microscopic level, there are loads of electrons whizzing around the atoms and molecules that make up any solid.
Right. This brings up an excellent point. The magnetic behavior of any everyday object is influenced by a fascinating combination of effects ranging from the level of particles to atoms, collections of atoms, and collections of atoms. First, individual particles. Unlike the everyday workings of gravity and electricity, permanent magnets can only be fully understood as a quantum mechanical effect, in much the same way that particles like electrons and quarks have fundamental properties called mass and electrical charge. Most particles also have another intrinsic property called tiny magnet. Just kidding, it's called intrinsic magnetic moment, but really that's just technical mumbo-jumbo saying that particles with electric charge also happen to be tiny magnets.
If you want to know why they're tiny magnets, well, you may as well ask, why are particles charged in the first place? Or why do objects with mass and energy attract each other gravitationally? No one knows. We just know that's the way the universe works.
Exactly, and since the 1920s, we've known that each individual electron or proton is basically a tiny magnet, which brings us to the level of atoms. An atom is a bunch of positively charged protons with a bunch of negatively charged electrons whizzing around them. The proton tiny magnets are about 1,000 times weaker than the electron ones, so the nucleus of the atom has almost no effect on the magnetism of the atom as a whole.
And you might think that since many, though not all, of the electrons are also moving, that like the current in a wire, they should generate magnetic fields due to that motion. And indeed they do. These are called orbital magnetic fields.
Except these don't usually contribute to the magnetic field of an atom. Here's why. Electrons in atoms are accurately and complicatedly described by quantum mechanics, but the gist of the story is that electrons congregate in shells around the nucleus. The electrons in any filled shell zoom equally in all directions, so the currents they generate cancel out and generate no magnetic field. These electrons also come in pairs whose tiny magnets point in opposite directions and also cancel. However, in a half-filled shell, all of the electrons are unpaired, and their tiny magnets point in the same direction and add up. meaning that it's the intrinsic magnetism of the electrons in the outer shell that gives an atom the majority of its magnetic field. So atoms near the side of any of the major blocks of the periodic table, which have full or nearly full outer electron shells, aren't magnetic, and atoms in the middle of the blocks have half-full outer electron shells and are magnetic. For example, nickel, cobalt, iron, manganese, chromium, etc.
Wait, but chromium isn't magnetic.
Ah, but just because an atom is magnetic doesn't mean that a material made up of lots of that atom will be magnetic, which brings us to the level of crystals. When a bunch of magnetic atoms get together to make a solid, they generally have two options. One is for all the atoms to align their magnetic fields with each other, or they can align their magnetic fields in an alternating fashion so they all cancel out. The atoms will do whichever one requires less energy.
That's why chromium, for example, is a very magnetic atom but a very unmagnetic solid, because it's one of the most anti-ferromagnetic materials that we know. Iron, on the other hand, is the namesake of ferromagnetism, so it is unsurprisingly ferromagnetic, or, in usual parlance, magnetic.
Sometimes. The last and final level of magnetism is that of domains. Essentially, even in a magnetic material where the magnetic fields of atoms line up together, it's possible that one chunk of the material will have all its atoms lined up pointing one way, and another chunk will have all its atoms pointing another way, and so on.
If all of these domains are of a similar size, then none may be strong enough to force the others to align with it. In which case, a piece of iron, for example, may have no magnetic field at all because of all the warring magnetic kingdoms within it.
However, if you apply a strong enough magnetic field from outside the material, you can help one domain expand its control over its neighbors, and so on, until all of the domains have been unified into one kingdom, all pointing in the same direction.
And now, finally, you can rule with an iron fist! I mean, magnet. It's magnetic because it's ferromagnetic and all of the domains are aligned.
Exactly. What's remarkable is that magnetism is a fundamentally quantum property amplified to the size of everyday objects. Every permanent magnet is a reminder that quantum mechanics underlies our universe. In order for an everyday object to be magnetic, though, it has to have a unified kingdom of magnetic domains, each made up of bajillions of magnetic atoms which also need to be aligned with each other, each of which can only be magnetic in the first place if it has an approximately half-filled outer shell of electrons, so their intrinsic magnetic fields can align and not cancel each other out. Not surprisingly, these criteria are pretty difficult to fulfill, which is why there are only a limited number of suitable materials you can use when you're building a magnet.
Or you could just run a current through any electrical conductor and produce a magnetic field that way.
But hey, why does that work in the first place? Click here to go over to Veritasium and we'll find out what special relativity and the speed of light have to do with electromagnets. I want to find out.
Like they said in the video, right? Since moving charges produce an electric field, and in an atom, electrons are just kind of whizzing around all over the place, they're making a whole bunch of magnetic fields, right? Now, in most materials, they move equally in all directions. So overall, what do you get? You get all those electric fields making magnetic fields, but they cancel each other out because it's completely random, right? But some atoms, right, called ferromagnetic, named for iron, ferrum, right, have their E- arranged in a way that their magnetic fields do not cancel, but align, okay? And those are those with the half-filled shells, like they said in the video. Again, you don't need to necessarily know that, but it helps build up some understanding that it involves the atomic structure here, okay? Now, that's not enough. All of those atoms then have to be arranged in a way that all of their magnetic fields align. And if that happens, then you can get a domain, okay? If that's still not enough, now all the domains need to align. And then if that too is true, you can have a permanent magnet. Okay, and so like it said on the video, you can actually apply an external magnetic field to try and influence the domains within a solid and align the magnetic fields that way. So I'll show you something really quick. Okay, so this is something called a magnetizer. Okay, how does it work? Well, like the name suggests, it can turn things that might not be magnets into magnets. The more common application of it, however, is, by physics teachers to fix their old magnets. Okay, now being a bit funny there, of course you can use this in industries a lot of the time, right? But this size of one is probably mostly for demonstrations and stuff. Okay, so I have here two magnets that have kind of been they've been sitting next to each other in a drawer in the back room in Mrs. Ellis's room. So I found them. They've been sitting at the bottom of a bunch of magnets, and over time what's happened is they've been influenced by other magnets near them, and they've kind of gotten you can see they're kind of backwards. Look at these. That's two south poles according to the labeling. Of course, it's not actually two south poles, because what's happening, those two south poles are attracting, right? Two south poles attracting. So that is a good way to know that, okay, something's not right here, right? One of those is not actually a south pole. Okay, so what this allows me to do is this is a magnetizer. It applies a very strong magnetic field, okay, and it can align all the domains in here that have clearly, over time, by being near other magnets, getting moved around, getting rubbed, external magnetic fields have messed with one or both of these magnetic fields and caused it to not actually be the way it was originally labeled when this ferromagnetic bar magnet was made a long time ago. So how do we do it? We put them in here, okay, and then this will apply a strong magnetic field, an external magnetic field, and what that will cause to happen is all the domains that have gotten kind of screwed up over the years, right, will be forced into the alignment I tell them. So I have to be careful when I place them in here that I do it right, because now I'm telling it to align the domains how I want them to. Otherwise, sure, I might align the domains, but if I don't align them in the way that I'm trying to make them agree with their labeling, then what was the point? Okay, so to do it, you kind of connect them here, okay? Notice right now they're actually not very strong at all, right? A little bit of stick. This one is actually pretty much nothing to it, okay? But when I apply, it's turned on, but I haven't started the magnetic field. So there's electricity flowing, but I haven't actually caused it to apply the strong magnetic field. And you can often kind of hear a bit of a, did you notice that? I don't know if it comes through on the video, but it's actually really satisfying. You can kind of see it. So I'm just going to pulse it with some strong magnetic field. And what's happening in there right now is all those domains are getting influenced by that external magnetic field and being made to fit the right way that they were supposed to be, or at least the way they were labeled when they were first made. So now notice how much harder that was than compared to before to actually pull it off. They're also kind of sticking in here a lot more because there's ferromagnetic materials in there, right? Okay, now I pull that out. Aha, there we go. I fixed it. Look at that. Not only have I fixed it, they're actually a lot stronger now. I kind of didn't show it before, but they were really hard to get to actually stick. They were kind of, not hard to get to stick, but they were close to falling off. They weren't holding on that tightly, right? And I fixed it because, there we go, right? They are properly repelling the way they should and attracting the way they should. Good. So this is actually quite a cool microscope image, a very powerful microscope. Take a second, check the scale, right? Check the scale. This much is 20 micrometers, so 20 times 10 to the power of -6, or 0.00002 meters, right? Very, very small, okay? So like, to give you a reference, even the smallest of human hairs, even the thinnest human hairs are about 50 micrometers, so 2 and a bit times bigger than that. So I want to be clear here, you might be, especially since the visual kind of looks similar to the video, be careful. These are not the domains, okay? The domains are actually the, I'll see if I can kind of point them out here. Notice the sort of stripes in there. This is kind of a domain, right? That's that dark part. That's kind of part of a domain, right? And then the light part, see how it's almost zebra-ish? The dark and the light are actually part of magnetic domain. So this is something we can kind of see on, yes, a small scale, but human hairs are pretty huge compared to atoms, right? So the result of something happening on a much smaller scale, but then just dialed up through all these kind of criteria to make it happen macroscopically. Okay, so based on what we know about domain theory, looking at these two, which is magnetic, right? Well, domain theory says that if all of them are aligned, all their magnetic fields can kind of become aligned, right? And so looking at those two options, definitely this one is magnetic field, or sorry, is magnetic, right? Is a permanent magnet as opposed to an electromagnet, which we'll talk about later. So this is something that would be permanently magnetic, such as iron or cobalt or one of the minerals, okay? So those little field lines within the magnet, right, suggest that this thing's North Pole, right, is here. North Pole is here. South Pole here, right? And so the field lines, whoops, that's wrong. The field lines kind of move like that, right? That. Okay, so use domain theory of magnets to explain how a magnet attracts a steel bar. First thing you got to know, steel contains iron, okay? So that means it is ferromagnetic. It has little domains that can get aligned properly, right? So if it contains iron, it checks off the box of having the half-filled electron shells that can even allow the atom to be magnetic, and then the atoms can end up aligning so that their magnetic fields don't cancel out. So how can a magnet attract a steel bar? Well, it can align the steel bar's domains, right? This is exerting a magnetic field. So as the magnetic field lines kind of go, right? Okay. They can align the domains in here so that now this has become a magnet with, hey, where would this thing's north and south poles be? Well, remember, they exit north, enter south. So this would be its north pole. This would be its south pole, right? Where would this thing's north and south pole be? Same thing. They exit north, enter south. So here's its north pole. Here's its south pole. And what do you know? Look at this. We have a north and a south pole next to each other. So what are the two things going to do? They're going to attract each other, okay? Now, common misconception is that this would happen to all metals, right? Don't forget, not everything is a magnet. It's actually pretty hard. There's actually very few things that are a magnet, right? Take something that's a magnet, go stick it to a bunch of metals. Chances are it actually won't stick to very much, right? And if it does stick to something, that thing is what we would call ferromagnetic. All right, very last thing for this topic, just kind of putting it together, what we know now about fields. So what is this question asking us to do? It's saying, given the magnetic fields illustrated above, the magnets will repel in diagrams. Well, which diagrams? So let's look. We got to figure out which ones are going to repel. Okay, we can do this by kind of looking at the fields, but honestly, probably the easiest way is to figure out which ones have opposite poles near each other and which ones have like poles near each other. Which of those two will repel when we have two like poles near each other, okay? So looking at this one, again, that field, the drawing of that field is kind of a hint, right? Are these things kind of going towards each other, being pulled towards, or are they pushing one another away? But first, let's just think about it in terms of poles. Okay, so what do we know about field lines? Where do they enter? Which pole do they enter? Which pole do they exit? So they leave north. So on this magnet, they're leaving. So that must be north. Okay, and they're entering south. All right, great. Leaving north, entering south. Now, let's just do that over here. This is kind of how we do this. So here, they're leaving here. They're leaving this side. So that must be north. And then they're entering this side. So there we go. That must be south. All right, what do we have here? Is that going to attract or repel? Opposite poles attract each other, right? So this will attract. So any answer with 1 is not our answer. Okay, let's look at 2 here. Okay, 2. So now we have, this is an interesting arrangement. Okay, leave north, enter south. So leave north. Where are they leaving on this one? Are they leaving this side or this side? Well, it looks like they're going that way, right? So they're leaving here and entering here, making that the north and the south. Well, let's go down to this guy here. Okay, leaving here, going here. So that's our north. Okay, leaving here, going here. That must be our south. Now, what do we have here? Okay, we have a south kind of lined up with a south and north kind of lined up with a north. So what will these do? They will repel. Okay, so 2 will be in our answer, right? Again, looking at the field lines, because it's important to understand that, notice if these were attracting, the field lines would be kind of connecting them, right? You would have a north going to a south. You can kind of look at those without and see that, these are kind of swerving away from each other, right? They do not want to go to each other, okay? Good. All right. Let's look at this one. So where do they leave? Where do they enter? Looks like on this one, they're leaving this side. So there's our north, okay? And then they're entering over here. So there's our south pole. Cool. Okay, now let's go down here. Again, look at those field lines. What does that make you think? But anyway, here, okay. Where are they leaving? Where are they entering? Well, look, this guy's leaving here. These are leaving here. So that's north. Okay, making this. They're entering here. They leave north and they enter south. So what do we have lined up here? We have a north closer to a south and a south closer to a north. So what will these things do? Attract or repel? Those are going to attract. Okay, so our answer will not have 3 in it. Okay, interesting. Again, look at those field lines. Compare that to 2, right? Look at the difference in how the field lines are drawn there. See how they're kind of connecting here, whereas here they're kind of swerving off each other, bouncing away, right? Saying, no, thank you. Okay, so test smartness, go now and see what your answer's got to be. But let's go ahead and do since we're not really writing a test here, we're trying to build our understanding. So again, look at those field lines. What does it make you think? But always the safer bet is to just figure out north and south, right? I'm just saying it's a good idea to also have that understanding of what the field lines tell you too, okay? But realistically, the safer bet is just figure out north and south, and then are they opposites or like that are next to each other? Okay, they're leaving here, entering here, leaving here, entering here. Where do they leave? They leave north. Where do they enter? South. Okay, over on this one, they're leaving here, so north, and they're entering here, so south. Okay, what do we got? We got a north lined up with a north. Again, look at those field lines. See how they're kind of pushing each other away when you look at them like that? They're kind of saying swerve, right? So, but again, opposites attract, like repel. That's the really important takeaway here. Opposites attract. So we have a north pointed at a north. Those are going to indeed repel. So what are our answers? Which ones repel? 2 and 4. So that wraps up kind of our basic introduction to magnets and magnetic fields and the topic 1. If you're wanting to work or solidify with some of the practice assignment 12.1, okay, you can get a bit of a start on that, although there's patchy bits that you can do at this point. So you can do part A, page 592, number 1, number 11, A, B, C, as well as part B, though realistically you may want to wait a bit for that until we've done a bit more and solidified your understanding a little more on this magnetic field stuff. I'm just going to also remind you folks, your textbook is actually really well written, especially for these chapters. It's quite a good resource, okay? So take advantage of that. It never hurts to just read through some of the parts of your textbook, especially the stuff that like this, where visuals and stuff like that help as well. And as always, study physics, right? Good for clear, concise, kind of 1 or 2 page summaries of topics. So just reminding you those things are resources that you can take advantage of.